Hello everyone, today our topic is air standard cycles. Air standard cycles are thermodynamic cycles where the working fluid is air, behave like an ideal gas. Air standard cycles idealizations are the Otto, diesels and dual cycles. These cycles differ only in the way of heat addition process. For example, in Otto cycle, heat addition take place at constant volume. In diesel cycle, heat addition take place at constant pressure. And in dual cycles, heat addition take place at both at constant volume and as well as at constant pressure. So here heat is added first at constant volume and then followed by at constant pressure. So now you will study about Otto cycles. So the Otto cycle consists of 4 internally reversible processes in series. 1 to 2 isentropic compression take place. See, compression take place here, and volume is decreased V1 to V2, and 2 to 3 constant volume heat additions, and 2 to 3 constant volume heat is added. You can see like this. And 3 to 4 isentropic expansion take place here. Volume is increases and expansion take place. And 4 to 1 constant volume heat transfer from the air, and heat is removed from the working fluid, or heat is rejected or Q out. So this is the process. Now the compression ratio. Compression ratio is the maximum volume divided by minimum volume. So here volume at V1, you can see here V1 is greater and V2 volume here is less. So V1 divided by V2, maximum volume divided by lower volume. So here V4 maximum volume and V3 lower volume. This is PV diagram. So V4 divided by 3 is the compression ratio. Now, ignoring the kinetic and potential energy effect, closed system energy balance for the 4 processes of the Otto cycle is reduced to give W12. Work done during compression is U2 minus U1. Through this equation we can find the work done during compression, and heat added at constant volume. Through this equation we can find, and work done during expansion. Through this equation you can find, and heat removed from the working fluid or heat rejected or Q out. Through this equation we can find. Now the thermal efficiency is the ratio of net work to the heat added. So the net work divided by added heat. So this is the efficiency, and the final equation is this. Through this we can find the thermal efficiency. Now the second cycle is air standard diesel cycle. The diesel cycle consists of 4 internally reversible processes in series, and the sequence of processes are the following. Process 1 to 2 is isentropic compression. Here air is isentropically compressed like this. Isentropic compression take place means entropy at state 1 is equal to entropy at state 2, and this is TS diagram. Now the second process is 2 to 3 constant pressure heat addition. Here heat is added at constant pressure. This heat is added at constant pressure, and in Otto cycle heat is added at constant volume, but here heat is added at constant pressure. Third process isentropic expansion. Here air is isentropically expanded, and entropy at state 3 is equal to entropy at state 4. And the fourth process is constant volume heat at transfer from the air. Here heat is removed from the air at constant volume. It can be so here. And this is all about the process take place in the diesel cycle. Now some term used in the air standard diesel cycles are the following. So first, compression ratio. Compression ratio is the ratio between maximum volume to the minimum volume. So here V1 is the maximum volume and V2 is the minimum volume. So the ratio between these two is compression ratio. Cutoff ratio. Cutoff ratio is the ratio between expansion volume to the clearance volume. So here at V3 the volume is expansion volume, and here at state 2 the volume is clearance volume. The ratio between these two is cutoff ratio. Now the energy balance used over the 4 processes of the diesel cycles are the following. So process 1 to 2, here from process 1 to 2 isentropic compression take place, and this compression work can be found through this equation. And process 2 to 3 constant pressure heat addition take place. So this heat added to the air can be found from this equation, H3 minus H2. So here constant pressure process, so we use enthalpy theorem, and if there is a closed system or constant volume process, so we use internal energy theorem U2. So here constant pressure, so we use enthalpy theorem. Now process 3 to 4 is expansion work. So this expansion work can be found through this equation, and process 4 to 1 is heat rejection process. Here heat is removed from the air or Q out. This Q out can be found through this equation, U4 minus U1. So here heat is added, there here heat is removed. Here is compression work, and here is expansion work. So this is all about the process take place in the diesel cycle. Now the efficiency. Thermal efficiency is the ratio of the work done by the cycle to the heat added. So this heat added take place between 2 to 3 process and work done, and the final equation comes here. Through this equation we can find the thermal efficiency of the diesel cycles. So this is all about the diesel cycles. Now the next cycle is air standard dual cycle. The air standard dual cycle consists of 5 internally reversible processes in series. The name dual cycle suggests that here the heat addition process of diesel cycle and Otto cycle both are placed in this cycle. So the sequence of processes are the following: isentropic compression. Here the piston is compressed isentropically. So this is the input work. And constant volume heat addition. So here heat is added at constant volume, like in Otto cycle. It is added at constant volume. Now constant pressure heat addition to the air. So here heat is added at constant pressure, like in diesel cycle. And this is isentropic expansion. So here this is the output work. Isentropically expansion take place during 4 to 5 process, and 5 to 1 is constant volume heat transfer from the air. So here Q out take place at constant volume. So this is all about the process take place in the dual cycle. Now energy balance over the dual cycles are the following. This is the PV diagram. Process 1 to 2 is isentropic compression. So this compression work can be found through this equation, or this is W input. This W input can be found through this equation. And process 2 to 3 is constant volume heat addition. So this heat can be found through this equation. And 2 to 4 is constant pressure heat addition. So this added heat can be found through this equation. So here we use enthalpy theorem. So you know that at constant pressure there is some work done and the piston expanded. So we use enthalpy theorem, and at constant volume there is no work done. So we use internal energy theorem U3, U2. So this output work or the piston done by the air on the piston can be found through this equation. And 4 to 5 is isentropic expansion. So this output work can be found through this equation. So here this is also termed as output work, and this is also termed as output work. So here the work is performed by the air on the piston, and here work is performed by the air on the piston. So this is termed as output work. And here 1 to 2 process is the input work. Here piston perform work on the air. So this is termed as output work. Input work. 1 to 2, during 1 to 2 process input work take place. The piston do work done on the air. And 5 to 1 is constant volume heat rejection. So this rejection heat out or heat rejected heat can be found through this equation. So this take place at constant volume. So this is all about the energy balance use over the dual cycle processes. Now the thermal efficiency for the air standard dual cycle. So this is the thermal efficiency, is the work done by the cycle to the Q in. So the work done by the cycle is the output work minus input work. So here output work you can see here 4 to 5 is here output work done, and here 3 to 4 is output work here is done. So the output work means that work done by the air on the piston. So this is the output work minus input work, and 1 to 2, during 1 to 2 the piston do work done on the air. So this term is the input work. So this is all about that. And here heat addition. So heat added during two processes, first at constant volume and second at constant pressure. So this is the sum of these two heat addition and the final equation we get, and through this we can find the thermal efficiency of the air standard dual cycle. So this is all about the gas power systems. Now in the next lecture we will study about the more cycles like Bertrand cycle. So that's enough. Thank you so much.